I have not just changed my name. I will give over very briefly and just take a few minutes to introduce the first use case because I already touched on it. So, but I will give an introduction. And of course, our goal with the eProcessor is to optimize the performance of our applications and use cases with it. And the applications are covering various domains from high performance computing over artificial intelligence, and we are touching on bioinformatics later. And of course, we are trying and we will exploit the different features of the eProcessor architecture, the out-of-order cores, the e-accelerator, the off-chip CNN accelerator that is provided, the level 2 cache optimizations, and of course, the new AI, the new instructions for AI and bioinformatics. Firstly, I want you to introduce to the smart home use case that is done at our apartment. It is to increase safety, health, and well-being of its residents and trying to make their life a little bit easier. And very often we have the problem, what is the interface with the environment? And we settled for a mirror that shows your image. And then you have some intuitive controls via gestures or with your voice. And then you can also use it to not just see yourself, but you can also display some information like when is your day going, your day schedule, the soccer results, whatever you are interested in, stock market. And that's a very quite cool way to integrate that in a smart home environment. In the smart home, we have, for example, intelligent door who has some input-output capability. We have a smart kitchen which can help you cook. Maybe good for most of the male participants here to have a little bit of help in the kitchen. We also have an intelligent chair for older people to get up, to get help while standing up, and to do some exercises while we are watching TV. Maybe we should get a call that we are sitting too long and getting some movement going on. So all of that is integrated in the smart apartment that we have, and the smart mirror is our central input-output device that we are using there, and we would like to use the eProcessor with it. So for different nets that we are using, to give a little bit of perspective, for face recognition, we are using mobile net trained with wider face dataset. For object detection, right now we changed from YOLO V4 Tiny to the normal YOLO V4. For gesture detectors, we have especially trained and changed YOLO V4 Tiny. And for speech recognition, we are using deep speech. As you can see, we are doing a lot of on-site processing. And that is one aspect that I forgot, but I think somewhere here it should be written, data privacy. So we don't want to use the cloud. We want to use everything. We want to process everything on-site. We want to go the quite normal way today, like sending all the data off to some cloud, doing the processing there, and then getting back the data. We want to do it on-site so that you have your own data at home and nobody else has really easy access to it. Another thing that we integrated for like cool demos is a AR style GAN that can make you look like a painting, like you know I don't only know the screen, I think it must be in English, and you can adapt that style to your image in the mirror, so you can make like look yourself a little bit more interesting than normal. When we look at the pipeline for the smart mirror, we have cameras, of course, and we are broadcasting the camera image to 2 microservers at the moment. We are using the YOLO to detect the objects and gestures, and then we are using a tracker with a Kalman filter to get the best results for the detections. For the images, we are looking for the images, and then in these found boxes, we are looking for the faces that we know. And with all that, we have then the person tracking, when we know which person is it, and what does he do with his hands, or I don't know, a cup in his hand or something. And then we can fuse all these detections and use them to make different decisions and change the layout of the displays we have and everything like that. Additionally, we have the microphone input, which is directly streamed into deep speech. And there then we have the speech recognition, get a transcript, and again, can make decisions out of that. When we look at the smart mirror and imagine what we could use the eProcessor for, of course, we can use the eProcessor for all the AI and CNN algorithms that we are using. We are using normal TensorFlow Keras-based stuff. The only thing we are looking for is good detection and recognition accuracy, so it's quite well suited for the hardware acceleration the eProcessor will offer. Another thing that is quite cool is the hybrid acceleration execution. So the out-of-order cores and the e-accelerator, which are tightly coupled and share memory, is really interesting for us. So doing the CNN layers on the e-accelerator and doing the pre- and post-processing on the out-of-order cores would be the best case for all of these things to tackle. Yeah, and in the end, we would like to use the e-accelerator, the systolic array it provides, and the reduced floating point precision. And I think at this point, I will hand over to Lluc, who hopefully can hear us and hopefully can say something.
Yes, I'm here. Can you hear me?
Perfect. So,
perfect. Thank you very much. So, well, first of all, hello everybody, and apologies for not being able to do this presentation in person there. I hope you're having a great time in Tampere. Yeah, so the second use case that we're going to present and of interest for the project is this surveillance border control. The idea of this application, well, the context of this application is that to use drones that help in doing the surveillance of maritime borders. These drones fly at a very high altitude and cover large areas, and they take high-resolution images that are colored and also can include thermal information. And the idea is to detect potentially very small targets in these images, like boats, etc. So this application has important constraints in the sense that the frame rate can be quite high, although it depends on the velocity of the drone and of the targets. Obviously, the power budget is important because the drones run on batteries, so you want to save, well, you want to have a battery life as long as possible. And yet, even with these constraints, the processing involved is quite complex for the segmentation and classification, and it needs high accuracy as well. And not only, there is various types of computation depending on the mission of the drone, which can be of different natures, from safety protocols to detection of illegal activities, etc. So you move to the next slide. So the application will use AI and CNN algorithms. They're going to be based on TensorFlow and Keras, which, as in the previous case, it provides good accuracy for detection and recognition, and it's very well suited for the hardware accelerators that we have in eProcessor. In particular, the surveillance border control application is going to also use a hybrid accelerated execution model where most CNN layers are going to be offloaded to the off-chip accelerator of the CNN accelerator. You see here it in blue. And then some other specific layers, as well as the pre-processing and the post-processing of the data and the results, are going to be done on the out-of-order cores of the eProcessor chip. One of the key features of the eProcessor architecture that is interesting for this use case and this hybrid execution model is the coherent chip-to-chip link, which comes in very handy for transferring data between the eProcessor chip and the off-chip accelerator. So that this facilitates things greatly. Yeah, and the use of the off-chip accelerator is going to be based on this historic array and some dedicated hardware structures, and all this is going to be managed from the TensorFlow and Keras descriptions. So you move to the next use case is the DeepHealth Toolkit. So the DeepHealth project is an European project that essentially targets automated diagnose of health issues for different biomedical applications. You have here production environment at the left. Essentially, medical doctors take medical images with MRIs or X-rays, etc. And well, they analyze it with some software platform that does a prediction of some potential health issues that are present in those images, right? That can be recognized with those images, and this gives feedback to the health professionals, including doctors, medical staff, etc. So for all of this to work, there is a training environment that you see on the right part of the figure, which is where the computation and all the computer science part takes part, right? So the idea is that the health professionals provide labeled images with well-known issues or health issues. And what the project does is to build a biomedical image dataset with those images that is used to train an artificial intelligence model based on two main libraries, EDDLL and ECVL. And there's a whole HPC and cloud infrastructure where some AI models are being trained. And these are then integrated in the software platforms that are used by the doctors in the production environment. So if you go to the next slide. Yeah, as I commented before, this DeepHealth Toolkit on the computational part, it has two main components. One is the European Distributed Deep Learning Library, EDDLL, which allows the definition of different neural networks architectures, and it supports multiple accelerators like GPUs, FPGAs, and CPUs as well. And it has a scalable design that is designed to scale well in large heterogeneous clusters. Similarly, the European Computer Vision Library, or ECVL, is the library that allows image manipulation and data exchange with the AI frameworks, and EDDLL in particular. So all the pre-processing of the data especially is done with this library. And it also supports accelerators like GPUs and FPGAs, etc. So these are the two main components of the training part of the DeepHealth Toolkit. And in the project there are different, I think 12 use cases, but in the eProcessor project we are focusing on two of them that are basically because they can be, we can use them with open data sets. One of them is the skin lesion classification, which uses a ResNet 50 model, and the ASIC data set. You have here 3 images on the left with different skin lesion types, I guess. I don't really know. And you also have another biomedical use case, which is the detection of pneumothorax using a SegNet model and the SIEM data set. And you have 3 example figures here on the right as well. So this is essentially the use case of DeepHealth. If you go to the next slide. As in the previous cases, the DeepHealth Toolkit uses AI and CNN algorithms. In this case, it's based on EDDLL, not the typical TensorFlow, Keras, etc. frameworks. This is done from the scratch. As other frameworks, it provides good accuracy and it's well suited for hardware accelerator. And we're going to use a similar hybrid accelerated execution model using the out-of-order cores and the E-accelerator for the CNN layers, using as well the reduced precision floating point in the E-accelerator, which is one of the key features we want to stress with this use case. To do that, we're going to do a specific port of the EDDLL library using the compiler intrinsics that are going to be provided by the compiler team of the eProcessor project. So if you move to the next slide, we have the bioinformatics use cases. these bioinformatics applications have become very relevant in the last years because the sequencing costs have dropped dramatically in the last years, way faster than Moore's law. So what the cause of what this has created is a situation where the bottleneck is now more on the processing part, not on the sequencing part. So accelerating the bioinformatics applications is more and more important. If you go to the next slide. So in eProcessor, we are going to consider application use cases that are commonly found in secondary analysis. These are one of these phases is the sequence alignment, which is very relevant in many bioinformatics pipelines. Yeah, and this includes algorithms like the Smith-Waterman Blotto and the banded version of it, and also a novel algorithm that is the wavefront alignment, WFA. Another application use case that we are interested in is the sequence database searches with the FM index, which is also very, very relevant in many bioinformatics pipelines. So in the project, we're going to propose some optimizations and adaptations for accelerators for these applications in particular, but the idea is that other applications and tools can also benefit from these optimizations. You move to the next slide. So first application is the Smith-Waterman Blotto. This is the classical algorithm for pairwise sequence alignment. And one of the issues of this algorithm is that it has a huge computational cost because it's quadratic in execution time and memory. Quadratic regarding the sequence length. So there is a banded version of this algorithm, the banded Smith-Waterman Blotto. The goal of this is to reduce the computation cost of the Smith-Waterman, but the algorithm is not exact. It's rather an heuristic, which is a critical limitation in certain analysis. And the idea of the banded is to avoid computing the whole matrix of the dynamic programming, but rather just focus on diagonal that go from top left to bottom right and define the elements to be computed. So you're leaving some elements uncomputed, and obviously you have this trade-off between the accuracy of the algorithm and how much computation you wanna do. So this is a classical algorithm. If you go to the next slide, a more novel algorithm for pairwise sequence alignment is the Wavefront Algorithm, WFA. And the biggest breakthrough here is that it reduces the complexity to n times s, where n is the sequence length and s is the error or the differences between the sequences. And in order to do this, essentially the WFA computes the elements of the dynamic programming matrix by increasing the score. So it doesn't have to compute all the elements of the matrix. And to do that, it changes the encoding of the matrix using offsets instead of scores, and introduces an operator that increases the offsets according to the number of contiguous matching characters in the sequences. So you avoid lots and lots of computations and reduce the complexity a lot. In the next slide, a brief explanation of the FM index, which is the final application use case of bioinformatics. The FM index is found in many bioinformatics applications that require exact searches into a database. There's been previous proposals like the suffix tree and the suffix array, but the FM index was a great breakthrough. First, because it reduces the space requirements by an order of magnitude compared to the previous approaches. It can fit the whole human genome in 1.5 gigabytes, which is pretty awesome. And this allows fast string search in the database. This algorithm has typical properties of HPC applications, like basically random memory accesses to a large memory footprint with poor data locality and little data reuse. And it also has some characteristics that are a bit more special, like the bit manipulations it requires, which are not typically found in other applications. So if you move to the next slide. For these bioinformatics optimizations, for these bioinformatics applications, sorry, we're going to use, we're going to optimize them for the eProcessor, also in a hybrid execution model with out-of-order cores and the eAccelerator that is on chip. So on the eAccelerator, we are essentially going to use vector instructions. And in particular, we're going to propose some new vector instructions for bioinformatics and use narrow integers of 1 to 1/4 bits. And all this is going to be coded at the application level with the compiler intrinsics provided by our compiler team. So if you move to the next slide, final use cases are the HPC. For the HPC, we have selected the Nash parallel benchmarks, which are very well known and widely used. These are traditional HPC algorithms, yet they are still very relevant in many scientific domains. And these include very diverse data structures, including dense and sparse matrices with different block sizes and different memory access patterns as well, obviously. So for this, we have 8 benchmarks in total and 5 input sets for each benchmark. So we are covering an important space of traditional HPC applications as well with them. In the next slide, the idea for porting and optimizing these applications in the eProcessor, basically, again, we're going to use the out-of-order cores and the accelerator. And we're going to do some, we're going to test the L2 cache optimizations here as well. So in the eAccelerator, we're going to use regular floating point vector instructions generated with the auto-vectorization features of the compiler. And for the L2 cache optimizations, we're going to use the scratchpad memory, the block management, and we're going to also perform blocking at application level, so we can also stress this part of the architecture, this L2 cache. Finally, in the next slide, just to conclude very fast, yeah, we have presented this set of application use cases that we're going to use and analyze and optimize for the eProcessor architecture. It covers various computing domains like traditional HPC, AI, bioinformatics, mostly. And this is a good collection to exploit the different features and the elements of the eProcessor architecture, like the cores, the accelerators, the L2 caches, the new instructions, etc. So that's all from the work package 3 side.